Swayam Prabha. Digital India. Educated India.
Hello and welcome to Lecture 9 on Special Relativity. In today's class, we're going to discover a powerful tool with which we can generalize our dictionary using the idea of the spacetime interval or spacetime metric that we've talked about. We will see that this allows us to define the transformations between different inertial observers using the concept of a group in mathematics, and this group is called the Lorenz group. And we will see that the Lorenz group tells us how different objects transform, and some of these objects will be generalizations of vectors that we're familiar with from rotations in space, but these will be rotations of vectors in space-time, so they will be what are called 4 vectors. Okay, so we'll have generalized transformations or generalized rotations of these objects which are called 4 vectors. And we will see that there are certain quantities which do not transform from one inertial observer to another inertial observer. And these are things that we call 4 scalars, okay, things that do not change under this generalized Lorentz transformation. And finally, we'll talk about the idea of tensors. How can we construct new objects that transform from one inertial observer to another inertial observer, but have more complicated rules than the transformations of vectors and scalars? So let's go back to an example that we've discussed. When we start with an observer in frame S and we move to a frame S prime, where S prime is moving relative to S at a speed v, or equivalently a speed parameter beta, which is v by c. Then we've seen that if we have coordinates ct, x, y, and z as described by an observer S, then we can arrange them in this way in a column vector, and we can ask how they are related to the coordinates of a space-time event as seen by an observer S prime, which we denote with ct prime, x prime, y prime, and z prime. And we've seen that the transformation is linear, okay, and the linear transformation matrix depends only on this parameter v, and we'll assume that S prime is moving with respect to S, let's say along the z-axis, the x-axis. And so if that motion is along the x-axis, the transformation looks like this. Okay, where gamma is 1 over the square root of 1 minus beta square. So this tells us the transformation between the coordinates in frame S and the frame S prime. Now what we've seen is, given this transformation rule for coordinates, there is a space-time interval. Okay, in this case it's the interval between let's say the point 0, 0, 0, 0 in frame S, that is time is 0, space coordinates are 0, and the space-time point with coordinates ct, x, y, z, also in frame S. And if we construct this quantity, okay, this quantity is what we call delta s square or ds square if t, x, y, z are infinitesimally small, and this is called a space-time distance. Okay, and what we've seen is if we calculate the same quantity in frame S prime, then we would get exactly the same number. Okay, that is, we would get the same space-time distance between these two spatial points, space-time points A and B. So that is, if we calculated the quantity c square t prime square minus x prime square minus y prime square minus z prime square, this quantity would also turn out to be the same. So let me just write this in infinitesimal form. So for two space-time points A and B, which are separated by an amount dt, dx, dy, dz. So let's imagine that this is at 0, 0, 0, 0. Okay. What's important is the separation between these two, not the absolute locations of A and B. We can define the infinitesimal space-time distance between these two infinitesimally separated points as c squared dt square minus dx square minus dy square minus dz square. And for an observer in frame S prime, these same space-time points would give us the same distance measure, but calculated using the coordinates in the new frame. Now, what we've done is we've started with a particular set of observers, that is an observer S and an observer S prime. And for these two particular observers, we have shown that the quantity ds square is invariant. But now we can turn this question around and we can ask a new question, which is, what is the most general set of linear transformations on the coordinates in frame S, okay, where S is some particular frame. That is, what is the most general set of transformations on CT, X, Y, Z linear transformations, such that the space-time interval between any two space-time points is preserved. Okay, so clearly the transformation that we've written down here is one such transformation which preserves this distance measure. But what we'd now like to ask is, are there other transformations that preserve the same space-time interval? And can we find all of them? So mathematically, what we're trying to find is transformations that take us to a new set of space-time coordinates. So this is some other generalized observer S prime, not the same as the particular S prime that we chose above. And we're looking for transformations which are linear, so therefore they can be expressed in the form of 4x4 matrices. Okay, so we're looking for 4x4 matrices. Let's call these matrices lambda. And this transformation with this matrix will lead to a new set of coordinates, CT prime, X prime, Y prime, Z prime. And we want these transformations to be linear, so lambda is independent of our space-time points. Okay, so this would give us the most general linear transformation, but we want linear transformations which satisfy a particular criteria. That is, we want the quantity that is this quantity to be the same as this quantity, okay, after transformations. And again, we can write this space-time interval using matrix notation. So let's write delta S square in matrix notation. It can be written as, we'll write a row vector, ct, x, y, z, 1, minus 1, minus 1, minus 1, and zeros everywhere else. Ct, x, y. Okay. And similarly, we could have written ct prime, x prime, y prime, z prime. 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, minus 1, ct prime, x prime, y prime, z prime. Okay. And what we want is, under this general linear transformation, we want this quantity, the space-time metric, to be the same no matter what choice of point we make for t, x, y, z, or equivalently for t prime, x prime, y prime, z prime. Now we can write this this space-time interval, okay, using these matrices, and we've introduced this 4x4 matrix over here. This matrix is called a metric, or measure of space-time distance, and this metric is denoted with the symbol G. Okay, so it's a matrix with symbol G, and this matrix is just the one that we've written down over here. So G is what we call the metric. Okay, metric or measure. Okay, so for any space-time point, if we want to know what is the distance between two space-time points, we would construct, for one space-time point, we would construct this column vector. This would be in frame S. For another space-time point, we would construct this column vector. This would be A. This would be point B. And we would take the difference of these two column vectors. That is, we would construct this quantity. And then finally, if we want to construct the space-time interval between the points A and B, okay, we would take, so let's call this a column vector V. So the space-time interval between A and B would be given by V transpose, that is, we make this a row vector, dot G, where this is matrix product, dot V. Okay, this would give us the space-time interval between the points A and B, and you can check that this would just be C square TB minus TA square minus XB minus XA square minus YB minus YA square minus ZB minus ZA square. Okay, and similarly, in the frame S prime, we would construct delta S square AB as V prime transpose dot G dot V prime, where V prime is this column vector. that is the difference of the space-time coordinates between the points A and B in some other coordinate system of S prime. Okay, so now what we're seeking, to put it in this mathematical language, is we are looking for transformations so that we get column vectors V prime, which are related to column vectors V. Okay, so V being this kind of column vector, the difference between two spacetime points. V prime being this column vector, the difference between two spacetime points in the new coordinate system. And we're looking for linear transformations of this kind, where lambda is our linear transformation matrix, such that the quantity delta S square, which is V transpose dot G dot V, is preserved. That is, this quantity should be the same as V prime transpose dot G dot V prime. Okay, so we're not just looking for any linear transformations, we're looking for linear transformations that satisfy this criteria. And this criteria should be satisfied no matter what choice of space-time point we make, space-time points A and B we make. That is, we want this to be true for any space-time points A and B, or equivalently for any B. Okay, that is starting with a column vector for any two space-time points, like this, and making a linear transformation of coordinates to V prime. We want to find the most general set of such linear transformations, such that this product of matrices, which gives us a single number, which is the space-time interval, is exactly the same as this product of matrices in our new coordinates. And so you can see that this criteria, plugging in for V prime over here, would just be V transpose dot G dot V is V transpose lambda transpose dot G dot lambda dot V. Okay, where I've used the fact that V prime is lambda dot V. Okay, again, this is a matrix product. This is a 4x4 matrix. This is a 4x1 matrix, and the result is a 4x1 column matrix. And the transpose of this equation is V transpose dot lambda transpose. Okay, so this is the condition that the matrices lambda have to satisfy for any choice of V. Or equivalently, if I write it in this way, okay, matrix products are associative, so I can group them any way I like. So let me perform this set of multiplications first. And what that tells me is that since this relation, the left-hand side and the right-hand side, are equal for any choice of V, you can just compare these two expressions and say that we want transformations such that G is lambda transpose dot G dot lambda. Okay, so we are looking for matrices lambda that satisfy this equation. Okay. That's what we mean by finding the most general space-time transformations that preserve the space-time interval between two space-time points. Okay, so now what we're going to do is we're going to look for a set of transformations from a coordinate system S, where we have coordinates for space-time points denoted as t, x, y, z. We're going to transform them to a new set of coordinates, ct prime, x prime, y prime, z prime, which are related to the old coordinates through this 4x4 transformation matrix lambda. And the matrices lambda satisfy the equation that we've written over here, where G is the space-time metric, that is, it's this quantity. This particular 4x4 matrix. Okay. Now, before we start looking for particular matrices lambda, I want to make a claim, which we will justify. That is, the set of all such matrices, or the set of all such transformations using lambda, set of all such transformation matrices lambda form a group, and this group is called the Lorenz group. Okay. So what is a group? Let me just remind you the mathematical sense of the definition of a group. So a group in mathematics consists of a set, a set of elements which we'll denote as lambda 1, lambda n. It could be a finite or an infinite set, and this set of elements has a group operation on it. That is, we can take any two elements of the set, and using the group composition law, this composition tells us what we would get when we take two elements of this group. Okay. Now, if you get back another element of this set, then you satisfy the axiom of closure. Okay. So that is, under the group operation, lambda 3 also belongs to the group. Okay, so this set, let's call it G, okay, is the set, and lambda 3 belongs to the set. That is, if I take a group operation where I take two group elements, compose them, then I get a third group element. Note that it's not necessary that lambda 2 lambda 1 gives you back the same element lambda 3. Okay, this is not a necessary criteria. So the operation has a particular ordering to it. That is, lambda 1 acting on lambda 2 need not be the same as lambda 2 acting on lambda 1. Okay. So the first property is closure. That is, when I compose two group elements, I get back a third element belonging to the same set. The second property is associativity. That is, if I take a composition of lambda 1 acting on the product of lambda 2 and lambda 3, since lambda 2 and lambda 3 belong to the set G by the closure property, lambda 1 acting on those should also belong to the set G. This should be the same as first composing lambda 1 with lambda 2 and then acting on the element lambda 3 and then seeing what we get. So this property is called associativity. And a group, the group operation should satisfy this property. The third property is the existence of an identity element. That is, within the set G, there should be an element which we'll denote as E, and this element E is such that if we take any lambda belonging to this set, okay, and compose it with E, we would get back that element. And it doesn't matter which order in which we compose them, this would be the same as E dot lambda as well. Okay, so such an element E, which satisfies this relationship for all lambda belonging to G, is called the identity element. This identity element E. And the fourth property is that there is an inverse element for every element lambda of the set, and this inverse element we'll denote as lambda inverse. Okay, this is a different member of the set than lambda, and the group satisfies the property that lambda dot lambda inverse is E, and this is also true for the reverse dot product. Okay, so for every matrix lambda, or every element of the set G, there is a matrix or another element lambda inverse such that this dot product, okay, is equal to the identity element. So these are the four key properties that the composition law of a group must satisfy. Okay, so to define a group, I need to specify the set and I need to specify the group operation. And as long as the group operation satisfies these four properties, then we can say that the set along with the operation forms a group. Now, there is an additional property that some groups satisfy but not all, which is the property of commutativity. That is, if I take two elements, lambda 1 and lambda 2, if lambda 1 dot lambda 2 is the same as lambda 2 dot lambda 1 for any lambda 1, lambda 2 belonging to G, then the group is said to be commutative. The group operation is said to be commutative, and the group is called abelian. Okay, so to give you an example of this, let's consider a group of real numbers. Okay, the group of real numbers that is what we call R. Actually, let's take a simpler group. Let's consider the group of integers. Which we'll denote as Z. So the set is all integers. So let's say starting from arbitrarily small negative numbers, going all the way up to arbitrarily large positive numbers. And the group operation is addition.